In this video, we discuss Fourier transform properties. First, let's look at linearity. Linearity means that if two signals are linear combination in time domain, their Fourier transform a linear combination as well. If signal shifting in time, for example, x t minus t naught, so that the signal has been shifted by t naught. If we take Fourier transform for this signal, then we have a phase shift in frequency domain. So this is equals to e to the power minus j 2 pi f t naught. So the phase shift amount is f t naught and x f. Convolution in time equals to product in frequency domain. We mentioned that before. And product in time domain, convolution in frequency domain. This is the modulation property we're going to use a lot in our system. So Fourier transform of ext, if ext multiplied by complex exponential e to the power j 2 pi f naught t, then the Fourier transform is shifted by f naught. And this can be, this is shifted in frequency domain, this is shifted in time domain. And we can look at these properties together. So therefore, if we perform Fourier transform of ext multiplied by cosine 2 pi f naught t, the spectrum is x f minus f naught plus x plus f naught, and then take half. What this mean? Means that the spectrum of x move to f naught and then to minus f naught. We sum them up, take half. That's the spectrum of xt multiplied by cosine 2 pi f naught t. This is a famous property of the modulation property we're going to use a lot. The scaling property, if we perform the scaling in time, x8t, in frequency domain, we're going scaling of 1 over a in frequency domain, and the magnitude is divided by absolute value of a. You can see the scaling factors in time domain and in frequency domain, they are inverse. So if we, in time domain, the time is scaled by a, the frequency domain is scaled by 1 over a. The property of Fourier transforms give us more tools to obtain more Fourier transform pairs. For example, we know this, we derived this delta t Fourier transform is 1 in frequency domain. Then using the duality property of the Fourier transform, if we have 1 in time domain, the frequency is delta f. What does this mean? If we have time domain, so this is a t time domain, everywhere is 1. What does this mean? This is a DC signal, constant, does not change at all. For DC, what's the frequency? The frequency is 0, right? So 0, delta f, f. So delta f, that's only has value in f equals 0. So that's the frequency domain. This is a time domain, and this is a frequency domain. I don't know if you can see or not. So this is a time domain, this is a frequency domain. From here, we can obtain more Fourier transform pairs. For example, we can obtain a Fourier transform that's curly f e to the power j 2 pi f naught t. This complex exponential. If we do Fourier transform, this will be equals to, we're going to use this property. Fourier transform of xt multiply e to the power j f naught t. So in this case, xt is equals to 1. 1, the Fourier transform of delta f. And using this property, modulation property, we're going to have the Fourier transform of e to the power j to pi f naught t, that equals theta f minus f naught. The same token, if we have this complex exponential, that equals theta f plus f naught, right? So these are typical Fourier transform pairs. Now we can obtain cosine 2 pi f naught t, the Fourier transform. Okay, we're going to use the Euler's formula, half e to the power j bracket, right? This is Euler's formula we use. Then using the linearity property, linearity property, linear combination in time domain. If we take Fourier transform will be linear combination as well. Okay, and using this result, we're gonna have equals to half theta f minus plus theta f plus f. So if we plot it, and this is this is f naught, it's supposed to be 0, minus f naught, half. So this is the spectrum of cosine signal. It contains two specs, two theta functions. The magnitude is half and half. We can see that it contains positive frequency and negative frequency. And as we said before, to obtain a real signal in time domain, we have to have positive frequency and negative frequency. They are symmetric here. All of these Fourier transform pairs, here, this one, and this, and this, are very important. We want to know